So we have virtual memories. So what is virtual memory? So suppose the physical memory space, that is the main memory space, is not sufficiently large. Okay. So we have to store the additional information in a secondary storage. So we have to get those data from the secondary storage into the main memory, and from the main memory to the processor to execute that. Okay. So for that we have a technique called the virtual memory techniques. How to transfer the data from the secondary storage device to the main memory, and from the main memory to the processor. So that the technique used is called as the virtual memory technique. Programming data into the physical memory when they are required the execution is called the virtual memory techniques. So for that we need virtual or logical addresses. So the secondary storage device, from there it is taken into the main memory. So for that you also have a hardware unit which is called the memory management unit, or the MMU. So this we can see through a diagram. See, you have the processor, you have the cache, you have the main memory, and you have the secondary storage device. So processor to cache, if it wants to send a write a data into the cache, or read a data from the cache, then what it does is it should give a physical address. So in order to give the physical address, what it gives is it will give a virtual address to the MMU, and MMU will will convert it to, the virtual address will be converted to physical address, and that address is given to the cache. And depending on that address, the data is read or written into by the processor using the data bus. Then this physical address, that the cache will give to the main memory, and the main memory and the secondary storage device, that will transfer the data through a technique called the DMA transfer. Now, how this virtual address is converted to physical address? That has a method called address translation method. So for that, you need to know a table. This is a block diagram. Like you have a base page table base register which will have a base address. Suppose the base address is just 0. Okay. So suppose this is a page table. It's just like you have a book and you have an index, and index will have the page numbers of each item or each topic that is written inside the okay. So instead of going directly to the page table and looking at the page number, what is done is we have an address, and to this base address you add the virtual page number, and that will give you the actual page number of the book. Okay. So suppose the base address is say 50. Okay. So suppose the first topic is in page 51. Then the base address will be 50 and virtual page number will be 1. So 50 plus 1 will give you 51, and that 51 is the first topic address. So 51 is your physical sorry. So yeah, you can find that item 51 by adding the base address and the virtual page number. So virtual page number, who gives? The processor will give. Virtual page number and an offset is given by the processor. So these are two fields, and of that only one field is given to this and this is added to get the page number. Now, this 51, right? That 51, that gives the page frame, and this page frame plus the plus means that appended with the offset of the virtual address. This offset will give you the physical address. Okay. So in order to find the page frame, you have to add the base address, page table base address with the virtual address from the processor. So we told about DMA transfer. Now what is DMA transfer? So DMA is direct memory access to transfer large blocks of data between the memory and the secondary storage device. You need this method called the direct memory access. So you're actually giving the control of the bus from the processor to an IOs, or the you can call it as the bus master. Okay, so you have a DMA controller, a circuit called DMA controller, which will have the access to the bus and not the processor for some time, so as to transfer this block of data. So how is this done? For that, you need to know some things. So IRQ is a bit called the interrupt request. IE is a bit called the interrupt enable. Done means the DMA transfer is over. Read bar, write bar means this bit, if it is 0, then write operation will be done. If it is 1, then read operation will be done. Then you have a starting address and the word count. Starting address is the first address from which the block of data which is to be transferred. That is the first address. From this particular point to so many word counts, it should be transferred. So this is a block diagram. Processor, you have the main memory, you have the bus, and you have the DMA controllers and the IO devices. So the DMA controller will gain access to the bus and it will start the data transfer. So suppose you have a processor and this is bus request. BR bar is bus. Just the complement sign just shows that they are active low signals. So if it is 0, then that is active. Okay, so DMA controller 1 gives, suppose DMA controller 2 is giving the request. It wants access to the bus. So what happens is it will give the request to the bus request to the processor, bus request line to the processor. So processor will give the bus grant signal. Bus grant signal will be given to the DMA controller 1 first. So DMA controller 1 has not asked for the bus. So it will pass on the bus grant signal to the DMA controller 2. So DMA controller 2 gets the bus uh, control. So that is shown as a timing diagram here. Bus request goes low. It is a active low signal. So when it goes low, high to low, bus grant signal is given by the uh, processor. So the first DMA controller does not need this bus grant signal, so it will pass on to the NES. It will make it to BG2 and give it to the DMA controller 2. So BG1 and BG2 are high, active high signals. That's why it's going high. It is changing. So the change means that it has there is a change. So high to low means the bus request has become active. Here low to high means bus grant has been made active. So the DMA controller 2 gets the bus grant signal, and at that time the processor will also give the bus bus busy signal will be made low, so that no more DMA controllers can give the request signal. Okay, so bus busy signal will be given, so that the bus request is made inactive, and after the transfer of data, the bus busy will be made, sorry, the this will be given to bus request, and the bus request will make it to active low, so bus busy becomes active, and then the DMA controller 2 will get the access of the bus. So here processor is the bus master, because bus master means it has control over the buses, and here the DMA controller 2 is the bus master, and after that again processor becomes the bus master. So that is bus arbitration in DMA control. So next we'll talk about IO devices. So input output devices, the processor needs to access the input output devices. And how does it access the input output devices? So this is the basic structure. You have a bus, and you have the processor, memory, and the input and output devices connected to these processor and memory via a bus. So suppose you have a program, suppose you have a program to access the keyboard. Okay, the user is typing some characters in the keyboard, and the processor needs to read the characters that is being typed in by the user. So we know that the keyboard is a input device, and the input device is accessed by the processor. How? Using a program. Okay, so in this program, first, yeah, there is a memory pointer that is initialized, then there is a status bit that is tested, that is whether a new character is coming in or not. So it is waiting for the character to be entered by the keyboard. Then when the character comes in, it is read. Then yeah, it is testing whether there is a data in the S out status, and as and when the data comes in, the character comes in, as and when the key is pressed, it should be displayed. Okay, so that is the program for this is the program for that. When a character is pressed in the keyboard, it is continuously checking whether character is pressed, key is pressed in the keyboard, and whenever it is pressed, it is displayed. Okay, so that is the program. So what I'm meaning to say is that if I'm accessing the input output device using a program written into the processor, then that is called a programmed IO. Okay, programmed input output. So we have a program which will help to read a character from the keyboard, and we have a program with it which will um, display that character which is being read in from the keyboard. It is displayed in the monitor. So that is an example for the programmed IO. Next, you have the interrupt driven IO. So interrupt, we have already discussed what interrupt is. So when a particular program is being executed, it is interrupted, and the processor will go to service another routine, another program. That is called a interrupt. Interrupt can be hardware or software. So if a hardware interrupt comes in, it will go to service the hardware interrupt. If a software interrupt is written as a code inside the program, then it will go and service that particular routine. Okay. So this interrupt can also be used to service the input or output request. Okay. So we'll see about that. So this is an example for the interrupt hardware. So you have the processor here, and these are some of the input output devices. Suppose a particular device gives an interrupt, that is these are modeled as switches. So if it is giving an interrupt, that is say a character is being pressed, so you want to access the character from the keyboard. So the keyboard, suppose this is your keyboard, and the keyboard wants to interrupt it. So what will happen? The interrupt request, INTR, is the interrupt request that will be given to the processor. How will it be given to the processor? The switch will be closed, and here the interrupt request will come, and that will be given to the processor. Just understand that much. Okay, interrupt request will be given to the processor via the interrupt request line. Okay, so there are multiple devices. So one of them can give, or multiple devices can give the interrupt request at the same time. So based on a priority scheme, that is device 2, device 3, maybe device 1 has the higher priority. So if device 1 and device 3 gives the interrupt request at the same time, the one with the higher priority will be serviced first, and then only the next interrupt will be serviced. Then when one particular device is being serviced, that is say a keyboard is being serviced, its request is being serviced, at that time suppose the processor does not want any more interrupts, then what it does is it will disable all the other interrupts. Okay, no other device can send a request simultaneously when the processor is servicing a particular device. Device 1 is being serviced right now by the processor. So device 2 or device 3, device 4, etc. cannot send an request when this particular service routine is being processed. If that is the case, then you go for disabling the interrupts. And after this device 1 is that routine is serviced, then it will again enable the interrupt so that any other device can send the request. So that is enabling and disabling the request. So uh, if multiple devices are sending the request, the processor should know who is sending the request. So one method is by vectored interrupt. That is, the device that is sending the interrupt, it will also send a code with the interrupt saying that I am this person. Okay, sorry, this device. Okay, so it is a unique code, unique to each device. So if device 1 is sending say 01, so 01, when it says 01, it means that device 1 is the one giving the request, and device 2, maybe it will send another code 02. So it will know from the code, the processor will know from the code as to who is sending the request. So that is vectored interrupt. Then you have the interrupt nesting, that is if it is allowed that multiple interrupts can happen. Okay, earlier we said that if one interrupt is being serviced and the processor won't take any more interrupts until this is finished, in that case, this nesting will not happen. But if nesting is allowed, mm, that means that when one's interrupt is being serviced, when it is serving a particular service routine, interrupt service routine, it will receive another interrupt. So from the first interrupt service routine, it will go to another interrupt service routine, then another interrupt service routine, as many interrupts comes in, and then it will return. So we can see it diagrammatically. See, here each device has interrupt request and interrupt acknowledgement lines. So each device can send interrupt request. It is not a single line, and the processor can decide on whom to acknowledge. So the processor will acknowledge the first device to give the interrupt request, and uh, then when it gets the acknowledgement, the device will know that its interrupt request will be serviced right now. So this is another method. See, here all the devices are giving the interrupt request via same line to the processor, and the processor will give the interrupt acknowledgement. It will give it to the device 1 first in this particular case. If device 1 has not sent the interrupt request, then it will pass the interrupt acknowledgement to the next device. And device 2 has not requested, then it will go to the next device. So the first device which will get the interrupt acknowledgement, that will take the interrupt. Okay. I mean, that particular device will be serviced first. So it depends on the priority in which the device is connected to the processor. Device 1 first, device 2 next, device 3 next, like that. So this is another method. Here you have two sets. Okay, so interrupt request, one line is this, and interrupt request another line is there. So you can have multiple sets like this. So if interrupt request 1 comes in, then it will send the interrupt request acknowledge 1 to this device, and this will continue and find the device which has requested it according to the priority. Likewise, if there are multiple requests, so it will send multiple acknowledgements too. So that is multiple requests from multiple devices.